Hello. I'm Big Kate, and I'm not good with mics. I'm your herald for this session. The plan was for a guy called Josh Lackey to speak, but apparently he's MIA, so he's not speaking. So we have Steve, and we have John, and we have their names. Sorry, David Hutton. I'm not up here. And I'll talk to you a bit about them, and that's on. Okay, fine. David here has extensive design experience and hacking experience. He's designed the BSD Air tools, has done extensive research in wireless, smart card and GSM design, and more importantly, has looking at high-speed crypto hacking FPGAs. He runs the Open Cipher program. Now, Steve here is a complete cipher to me. I have not a clue about him, and apparently he wants to keep it that way. The talk is about, okay, we have the talk, with lots of GSM support for GNU Radio. David and Steve here are here today to present a technical presentation on the current state of GSM security. The plain cover is what it takes to get past open air encryption, monitoring unencrypted GSM, various attack mechanisms. They're planning to make some code presentations, and with the goal of making a feasible A5 cracker. What they would like to get out of this is some discussion about this, look at and to look for suggestions and feedback, and their plan is to talk for a while, and we'll then have a Q&A at the end, and I think that's me done.
Thanks.
Testing. Whoa. Okay, so I'm David Holton. She already introduced me, and wow, it's very echoey in here. Yeah, and so this is Steve. Basically, what we're going to do is he's going to talk about the Gsm Scanner Project for the first half of the talk, and then I'm going to show you how to break GSM after that. So, I guess go ahead, Josh, or sorry, Steve.
All right, thanks a lot. So, as David said, this talk is split into two halves. I first explain you a little bit about GSM, about the security in GSM, and then David will tell you about how to crack A5, the encryption algorithm of GSM. And first off, well, let's get rid of this slide.
Next one?
Directly, yeah. Let me tell you about the Gsm Scanner Project, or we renamed it to the Gsm Software Project for legal reasons. If you have a software, it's legal. If you have a scanner, it's not. So first off, the Gsm Software Project, we started in January 2006. So we only started this year. And there are a couple of reasons why we started this. Well, first reason, people said, you know, no one has ever done this before. Great. People said, it's probably very hard to do. Great. And then most important, they said, you'll probably piss off a lot of companies. Oh, great. We want to do that. That's really great. Yeah, so we decided, let's get our heads together and think about how can we receive GSM signals. And we have a couple of methods, and some of the methods I'll present today. And yeah, let's get started. Next slide, please. GSM. GSM stands for Groupe Spécial Mobile. This is French, and no one really knows why they named it that way, but that's how it is. And it's a digital mobile communication design or protocol. It was designed in the 80s and became live in 91, I think. It currently has 2 billion subscribers. That's 2 billion subscribers worldwide. So it's the largest mobile network ever. And, well, I forgot to mention, this is a public project. All what we do is published on our website. You can read about it, and you can participate in this project, you can join our mailing list. And there's a very important reason why this is a public project. And this is the first question you should ask me later, okay? So don't forget, later on ask me, Steve, why is this a public project? All right, let's get started. Let me tell you a little bit about the GSM network. This is a rough idea how a GSM network looks like. You have a mobile phone here, you have a base station, you have a lot of computers, base station concentrators, blah, 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 and then you have this, the AUC. This is the authentication database. This is where all your secret keys are stored in, okay? So in this talk, I will concentrate on this one and on this part. The rest, it's just hardware we don't care about. Let's get started. Okay, GSM uses base stations, and you probably have seen them sometimes when you look around and you see these antennas, and these base stations are combined into clusters. And each base station has a maximum reach of 35 kilometers. 35 kilometers. This is from here to Berlin, is that right, roughly? So if you're sitting here with the receiver and someone in Berlin is doing a phone call, yeah, you can receive him if you're lucky. Okay, that's how far it goes. Let's go to the next slide and I'll show you some pictures of what the base station looks like. This is how a typical base station looks like. You have usually 3 antennas, and each antenna is a directional antenna with a 120-degree angle. So you have a mast with 3 antennas, each of them pointing into one direction, covering all the way around. I'll show you another pictures. Sometimes you don't see the base stations. There's a base station in this picture. It's this one. They sometimes hide base stations in a tree because people complain how they look like and they don't like to have them in their nice view. So this is 100% artificial tree, metal, concrete and plastic, and at the top there's a base station. So look around when you go to the forest now. Don't just watch for animals, watch for base stations. Now, let's go to the other side of the part. You obviously have the base station, you have a receiver. What you have to realize is that your mobile phone is a very high, sophisticated computer device that can receive radio signals, okay? And your mobile phone, in fact, has 2 processors. It has the baseband processor and the application processor. So the application processor is usually where your operating system runs on, Symbian, if anyone heard of this. This is where your calendar runs on. This is where all the user interface, all the games run on. And then there's interesting stuff, the baseband processor. This is where the antenna is connected to. This is where the entire secret Nokia stack runs on. In fact, someone from THC 2 years ago managed to make a memory dump of this baseband stack, and I think it's floating somewhere around a BitTorrent. So if you look for it, you can take a look at yourself. Okay, this is the basic design of a mobile phone. 2 processors, baseband processor, application processor. This is the part we're interested in. This is the secret in there. Let's get to the next one. Okay, let's start with tracing. There are many different methods how you can trace GSM signals. One of the easiest methods is to use a standard Nokia phone. Lucky for us, Nokia sent one of the phones with debug symbols enabled. For 2 years, they shipped a phone with debug symbols enabled, with the whole debug functionality enabled. So what you do is you plug this phone to your computer, use a specialized software which is available on our website, and you put it into a trace mode. And this mobile phone starts giving you all the traffic it receives from everyone. Okay, so it's all the traffic on the beacon channel. Okay. It is a little bit limited. It's not as powerful as a USRP, but we get to the USRP later. But this functionality helped us a lot to see what we tried to benchmark it against the USRP. And later on, I show you an example trace of how the trace looks like. Okay, let's see the USRP. Okay, this is how the USRP looks like. And maybe you've seen the previous speech, the GNU Radio Software Project. And well, it's just an amazing device. This device can receive anything from 0 to 3 gigahertz. Anything. Doesn't matter where you tune it into, you can receive it. There are people who wrote a GPS receiver with it. There are people who wrote software to receive all kind of television from it. There are people who wrote software to receive all kind of, well, everything you can receive. But no one ever did GSM, because GSM is just horrible complicated specifications, and no one wanted to get into it. You can program it with Python, so it's really easy. It's all open source. The device costs roughly, I think, $800 US. So you can get one, play around with it. Let's go to the next slide. And yeah, let's go into GSM a little bit. How's GSM designed? GSM works on 4 different frequency bands. This is, sometimes you've heard about this, like a 3-band mobile phone that works in almost everywhere except the countries where you wanted it to work in. Or now there's available the quad-band phone, and that should really work everywhere except where you don't have coverage, but it should really work everywhere. And basically it operates on these frequencies. You have an uplink frequency and a downlink frequency. And the design is very simple. The mobile phone either receives or it sends. It never does the same thing at the same time, which makes our life much easier because we only have to deal with one thing at a time, either receiving or sending. And the great thing is also the receiving part is on one frequency band and the sending part is on a different frequency band. So as long as we stay tuned into one frequency, we are sure on this what we get is all traffic from the base station. Let's take a look at GSM 900. You see that it starts at 890 megahertz and it goes to 915 megahertz. That's 25 megahertz. And each channel is 200 kilohertz wide. That gives us 1,000 channels. Now think about this, 1,000 channels. This means if 1,000 people do a phone call at the same time, GSM is blocked. You can't do, it's a DOS, okay? If 1,000 people, if you have 1,000 phones and you initiate a phone call at the same time, no one else in your area can make a phone call. That's how limited GSM is. Okay? Let's go to the next frequency. Obviously, okay, I have to clarify this. You can be locked into a base station, but you're not assigned a channel. When you're locked in, you're camping on a beacon channel, that's how it calls. You're just listening to the base station. But then when you initiate a call, you're assigned a dedicated channel. And there are only a maximum of 1,000 dedicated channels. So if 1,000 people do a phone call, everyone here in the camp, no one else can do a phone call. Great. Okay. I talked about this already. Send or receive. We have the beacon channel. We have the dedicated channel for traffic and SMS. This is something new for some of you. SMSs are encrypted, at least in Britain and Germany. It is optional to the mobile operator if he decides to encrypt SMS or not. Wherever we checked, it was encrypted. Unfortunately, and that made our life very hard, there's something called channel hopping. So every GSM burst lasts for 156.25 bit. Well, if you're a computer scientist and you read 2.2.5 bit, you say, oh my God. But if you're an RF engineer, you say, okay, no problem. And well, we talk about this later, okay? It's actually no problem. But one burst is that long. It's 156 bit, and not all these bits are actual user bits. There are only 52 bits, usable bits in there. The other bits are synchronization bits and tailing and guard bits and whatsoever. One burst only lasts 0.577 milliseconds. And a GSM message is made up of 4 bursts. You need 4 bursts to generate one GSM message. And a GSM message can be a message like, I want to initiate a call, or I want to initiate a cipher, or please tell me where this mobile subscriber is, or please hang up this call, or please hang up my call, or stuff like this. And we talked about this earlier. You have 1,000 channels, and they are divided into time slots. So on one frequency band that is 200 kilohertz wide, you actually can have 8 dedicated channels. These are 8 time slots. So for the first 156.25 milliseconds, it's time slot 0, and then it's time slot 1, time slot 2, time slot, and so on until time slot 7, then it repeats again. 51 bursts form one multi-frame, and well, that's just some idea how it works. Let's go to the next slide. I'll give you some example of what we actually received with the Nokia phone, okay? This Nokia phone, actually, I bought my Nokia phone on eBay, and funny enough, I paid €1 on eBay. The shipping cost €8, okay? So I paid 8 times for the shipping than for the mobile phone. And I had to buy a special cable, and that cost me €12. So the mobile phones are quite cheap, but the cables are expensive. We've first this was cracked by some Russian hackers in 2003 that found out, oh, the Nokia mobile phones actually ship with debug symbols. What we wrote is a program that can actually decode this GSM message according to the specification, which are really horrible. And I'd guide you through some example traces that we did. And this is an example trace of, I think it's initiating a phone call. And yeah, let's see how this goes. Paging request first is done by the base station, and asked for the mobile phone. Hey, mobile phone, where are you? Are you there? And yeah, let's go on to the next one. And at some point it tells the mobile phone, there's something happening for you. Please go onto this dedicated channel, it's SDC/8, whatever, and just get onto this channel and tell me when you're there. And let's go to the next one. And then it says, mobile phone, please tell me what your identity is. And now you have to realize the GSM specification says that your IMSI should never ever be sent over the mobile network, okay? And this is pretty much the first trace that we did. So let's go to the next slide. Oh, no. Oh, who thought that? Who thought that? Like the first trace we did and we see already the IMSI? Well, fine enough. Okay, so this gave us hope. Basically, it's the first trace that we did. We opened, I mean, no one ever has done this before. No one ever verified what these companies are doing, what the mobile radar are doing. And we opened that door that much, right? And what comes out is already shit. That's great. That gave us a lot of hope. Okay, so we see the IMSI. The mobile phone says, this is my IMSI. What do you have for me? And the BTS says, yeah, I have something. And actually, I support the encryption A5/1, which is indicated by the bit 0, and I support A5/2, which is indicated by bit 1. You know, no one knows why. And yeah, that's it. Then the mobile phone responds with, that's great, this is my random number. No, sorry, this is a base station actually. Sends a random number to the mobile phone, because the mobile phone has to authenticate itself, tell them, okay, that's really me, and you can charge me on my calling plan. And the mobile phone responds with an address. And at that point, the mobile phone is fully authenticated and is allowed to do a phone call or receive a phone call, or is allowed to send an SMS. And the ciphering is initiated. Cipher chosen by the mobile phone is A5/1, starts ciphering. From that point on, everything is encrypted. Now, the good thing about the Nokia Trace Mobile, in difference to the USRP, is that the Trace Mobile gives us everything after decryption, okay? So the USRP, when we tune in to a base station, we only see the encrypted messages. Now what the Nokia Trace Mobile gives us is after decryption. So we can actually see what are the actual packets compared to what do we receive on the USRP and what do we actually receive on the mobile phone. And we can compare these packets. And that helped us a lot performing our A5 attack, which David will explain later. Cool, and of course we already sent the IMSI, which is the International Mobile Subscription Identification. It would be a shame if we not sending the IMEI, the International Mobile Equipment Identification, okay? So actually everyone also knows what kind of handset you're using, which is quite good. And there's another thing. Did anyone ever lost their mobile and you try to ring the mobile operator and you tell them, yeah, I lost your mobile, can you tell me where they are? And they tell you, oh no, you can't, you have to buy a new one. That's bullshit. I mean, your mobile every time transmits where it is. It transmits its identification and it transmits where it is. The mobile operator knows very precisely 200 meters where your mobile phone is located. Okay? So this is a big lie for mobile operator that they don't know where you are. 200 meter precise. And if you're a little bit tricky, you can get it to a couple of meters precise. Okay, cool. Let's get on. Okay, security in GSM. This is Gsm Network. We have seen this before. And this is where the security happens. Let's go to the next slide. In GSM, the only part that is encrypted is the air part. As soon as it hits the base station, from that point on, everything is clear text. So anyone with access to the base station can plug into the switch, and there's a monitor port in the switch where you plug in your Windows laptop, and you have a special software, and you can listen to any traffic, okay? And this base station usually is protected by padlock or, you know, something like that. It's not protected. They're just anywhere in the forest. You've seen them. They're in the forest. Okay, this is encryption. And this encryption was already broken in 98. Ah, okay. This encryption was broken in '98, but how was it broken? The encryption was broken by people from the university, and from people from the university, they say it's broken if you can crack it in 1,000 or 2,000 years, and it's declared broken. But practically, you can still not read it. So actually, what we came up with is the first ever attack that only requires the first 3 or 4 GSM frames to crack a GSM conversation. All other attacks available require at least 2.5 minutes of conversation. We only require a couple of milliseconds, really. But David will tell you more about that later. All right, let's go on. Yeah, GSM security, A5, A2, it's a weaker algorithm. Some historical background. Initially, the countries were undecided if they should use strong encryption or weak encryption. France didn't want to have any encryption. Germany wanted to have strong encryption because they were bordering to the Soviet Union. And they decided, yeah, so we give some countries A5/1, the strong encryption, and for all people who doesn't want it, we give them a weaker encryption, it's A5/2 or A5/nothing. Okay, mobile operators always know your pre-shared secret. There's not a session key negotiated, it's always a pre-shared secret, which is in clear text stored in the mobile operator database, okay? It's clear text stored. Anyone with access to the base station can read your traffic. Anyone. And this is something that people don't realize. Past conversation can be decoded. If you throw away your SIM card and someone before recorded this encrypted traffic and he gets access to your SIM card, he can decode all the traffic without a password, without a PIN, without anything, okay? So never again throw away your SIM card, burn it or eat it. Never throw it away. People can listen to what you said in the past. Let's go on. Okay, this is the last slide that I have before I hand over to David. And I want to talk a little bit about what we're trying to achieve with the USRP and with the Gsm Scanner Project. We want to go into sending. Right now we can only receive. If we can send, hell yeah, we can have a baby cell. We can create our own pirate GSM cell. We can offer people free GSM calls in that cell. Well, on 35 kilometers, quite a big cell. Covers Berlin. This would be quite nice to have free calls there. We can do some, security stuff, man-in-the-middle attacks, and actually we can scan for phone numbers, like which phone numbers are in my area. We can brute force, or we can play with accessing the database of a mobile operator. We can have free calls, or we can track people where they are. Oh, actually, sorry, tracking people we can already do. We can already find out with just one USRP where you're located to roughly 200 meter precise. So with one USRP, we can already track people and see where they move to. And yeah, that's me. Thanks a lot. Later on, we have some questions, and I hand over to David, who will tell you how we crack A5. And that'll be fun.
Thanks a lot, Steve. So with the A5 cracking project, just to give you a brief intro here, when we were looking at starting this project, we were looking at only practical attacks we could actually implement and could actually crack conversations that weren't, multiple minutes long, and something where we could actually just drop it somewhere and then maybe record conversations, and within a reasonable amount of time actually be able to decode them and listen to what people are saying or sending SMSs and stuff. So originally we only looked at ciphertext only attacks, and a lot of these attacks seemed like way too complex and required a lot more time for the over-the-air capture than we really wanted. And so we actually ended up finding out through Steve's research that there's tons of known plaintext. The first 4 packets are entirely known, and so that equates to 456 bits of entirely known plaintext. And so then after we found this out, we geared straight towards just known plaintext attacks on that single, 4 packets that are sent out at the beginning of the conversation. So we researched a few different attacks. If you guys are familiar with any of these GSM attacks, there's this Anderson, Rowe, and Keller attack where I'll cover it a little bit more, but it's essentially taking the the output that you know straight out of A51, and then using the data that you know to basically find information about the registers inside A51. And I'll get into that a little bit more. We also looked at doing pre-computation because we're essentially brute forcing around 64 bits, which is a lot of bits. And if we could possibly build a rainbow table for this, then it would reduce our real time, you know, of the actual attack. And so we borrowed some things from other people and kind of melded it together to make it fairly practical for what we're looking at. And both of these attacks, we are actually accelerating with FPGAs. So if you happen to have an FPGA board, then you'll be able to speed it up and make it actually happen within, you know, a matter of minutes instead of days or years or whatever. So looking at A51 internally, I'm just going to describe how it works here. You have these 3 different shift registers here, and and essentially how it works is whenever this whole thing is clocked, it looks at these clocking bits, 10, 10, and 8, and then it finds out the majority of like which ones agree with the majority. So like if all of these are 0, then all of them are clocked. If just these 2 are 0, then these 2 are clocked. If just these 2 are 1, then those 2 are clocked. And then this one is not, like, because it's only the majority ones that are clocked. And when they're actually clocked, they end up taking these different tap points in here. So 18, 17, 16, and 13. They're all XORed together, and then they shift in on this side. And then this bit comes out and gets XORed over here. And this is the actual output of A51 that gets XORed with your actual plain text. And that's how everything gets enciphered. So to actually like mix in the key into the shift register, you take your 64-bit key that actually comes from the SIM card, and then you actually feed it in over here. And so on the first clock cycle, you'll take the first bit of the key and then XOR it in with you know, those bits, which should all be 0 initially. And they get fed in through here. 0 bit gets fed in through here, and so on. And then you you know, go bit by bit and start clocking in all 64 bits of the key. Then you take this frame number, which is unique to the frame, and it's 22 bits. And then that is actually kind of like an initialization vector, and it's sent in plain text in the frame. And that actually gets mixed in the same way that the key does. Then it actually runs, after it mixes in the 22 bits, it actually runs it for 100 clock cycles to just mix everything around inside the registers. And then after the 100 cycles, it actually starts clocking it forward and generating essentially like pseudo-random output out the other side based on the key. And that gets XORed with the plain text and sent out. So this Anderson row attack basically works on this premise that the bits that are sent out over here, if you know the actual output of A51, you can guess these 2 registers, and essentially this third register, or one of the registers, will kind of be like parity, where like if you know this bit, and that bit, then you can calculate this bit down here because it's just an XOR operation. So that can be reversed back. The only tricky part with this is that with the majority clocking, it makes it somewhat of a one-way function. So when you're actually like reverse clocking this, you have to kind of guess what the clocking bits are here, and I'll go over that a little bit. So yeah, the output bits are related to the register bits, and essentially you're basically brute forcing these clock bits down here, and trying to find out the right clock bits that will actually generate that output, and there's a couple things you can rule out, use to rule out different possible bits inside the third register. And how this works is that, like for example, if this register down here isn't clocked, and you kind of hypothesize that this doesn't match the majority here, then this bit, you know, should match up with the known plain text over here. And so if this bit changes and these match up, then it turns out that it actually doesn't clock it. And I'll put code up later so you can actually, you know, take a look at it and see how it works. but it's essentially just using that to generate parity and then trying to figure out logically like which possibilities work and which ones don't. So with enough known plain text, you'd be able to resolve all possible R1 and R2 pairs down to a valid R3 register. So what this does is, since you only have to brute force R1 and R2, it reduces it down to a 41-bit problem instead of the full 64-bit. And so it's essentially 2 to the 41 times around like 6,000 clock cycles for the third. So it's a pretty big shortcut. I've implemented this on an FPGA, and it takes around 6,000 clock cycles for it to run. And I've been able to fit 100 cores on an FPGA running at 100 megahertz. So it'll do about 1.6 million tries per second. And a single FPGA will be able to brute force a key in about 15 days. 100 FPGAs will do it in 3.6 hours. So if you guys have a bunch of FPGAs you have laying around, you can pull them together and try and crack this. PCs will take a huge amount of time. I haven't spent a whole lot of time trying to optimize this, but I can show you a demonstration later of how the speed compares between FPGAs and computers. So I'll do a quick demo of this so you guys can see how it works. Yeah, can you guys see that okay? Sort of. Yeah. Okay, so I have this program where it actually takes an R1 and an R2, and then you put in the known output of A51. That's a typo. It says R3. Just forget about that. Let's see here. Where did I put that? Oh. So yeah, I can just run this with these different values here. And yeah, so oh wait. Okay, for some reason that isn't working right now. So, but I'll actually just run this demo Perl script that I know that works here. So let's see what this does. Oh, weird. Oh, okay. Okay, so this takes in. Oh yeah, there we go. Okay, so right up here you can see the A51 thing. That's basically the key right there. FED CB A98, and 134 is the frame number. And so that right after the key is mixed in, this is the value of R1, R2, and R3, right below there. And then after like everything's mixed in and it's actually generating real A51 output, then there's R1, R2, R3, and this is actually what it outputs here. And so if you end up feeding in a valid R1 and R2 into this reverse sim application and the known plain text, it'll generate R3. And so all you have to do is brute force R1 and R2, and this should be the only one that ever returns true, like when you use that program. Then if we look down here, so assuming that that's essentially how we get R3 with the known plain text, or get all the registers, then I have this other program that'll reverse clock the 3 registers back to the original registers after the key was mixed in. And if you know the state of the registers after the key was mixed in, then you can clock that forward with whatever frame number you have and generate the same output, decrypt any packets or transmit any packets for that frame number. So so this reverse clock thing, it essentially tries to clock the registers backwards, and when you clock it backwards, because of the majority clocking, you're going to end up with many different possible clocking possibilities. And so with these 3 different registers, it turns out that you have all these different possibilities that of register states that could end up resolving to those, after 100 clock cycles. So how we roll this out is that since we have 4 different frames with 4 different frame numbers, if you actually crack 2 of the frames and then run both of them through this reverse clocking, then so right here I'm doing the same thing with frame number 135, where we generate the output for frame number 135 and then run it through this whole same process. And then we end up with these different possibilities for the reverse clocking. And then you just look to see which register states match up between the two, and that's the valid one for that key. And so here's actually the valid state right here, you can see. And so with those registers, that's essentially the same thing as the A51 key, and you can decrypt any conversations with that. And we'll be building in support into the USRP Gsm Scanner Project. So once you plug these values in, then you can decrypt any traffic that you want. So yeah, this basically just talks about how to reverse clock the A51 registers. And yeah, you just narrow down the possibilities. So yeah, this talks about the 2 packets also. Now, going on to the Pre-Computation Attack. What we do for this is if you have 64 bits of output of A51 anywhere in the stream, what we want to do is just reverse that back to the internal state of A51 so we can run it through the reverse clocking algorithm to get back to the state right after the key. And so we basically look at this like it's a one-way function, similar to like landman or any sort of password hashing functions, where they try to make it so it's a one-way function out to the output, and we're just trying to reverse back from the output to the internal state. And so we were looking at doing a rainbow table implementation to try and speed this up. And so we decided to focus on building a table of 2 to the 58, which I think is one of the largest rainbow tables anybody's ever generated. The landman rainbow tables are roughly around 2 to the 37, and so this is dramatically larger, almost 1 million times larger than a landman table. And if you look at this, it's 2 to the 56 is actually 1/64th of the entire key space. And because we have like all these packets, we have 4 packets, and each packet is 114 bits. So we actually have lots of different chunks of 64 bits inside that. If you take 114 minus 64, then you actually have quite a few bits to play with that you can possibly reverse back. And so we have a really good chance of actually finding a key for those 4 packets with just 1/64th of the key space. So can I see a show of hands of who knows how rainbow tables work or anything like that? Okay, cool. So this will probably be a really bad explanation, but I'll try to give it my best. The really basic time-space trade-off is you have a one-way function where it only goes a single way. You just have an input into a function, you get an output, and they try to make it so you can't go the other way. And so you need to find basically the input that created the output that you have. So the really naive implementation is you go through, try every possible input, and create like a huge table, and then you search through all the outputs in the table to find the one that matches, and then reverse it back that way. The really basic time-space trade-off implementation is you kind of do it the same way, where you have your one-way function, and you feed it through the one-way function. On the other side, you create a mapping of your output back to another input, and that's called a reduction function. And then you feed it through another one-way function, and you create a long chain of these. And what that gives you is you only have to store the start and the end. And then when you actually want to figure out how it works, when you actually want to do the real-time attack, you basically create a chain from whatever output you have, and you find let's see here. So like if you have an actual value that's inside the chain somewhere, then you can just start creating you know, chains ahead of that at varying lengths, and then eventually you're going to find an endpoint, and so you just like go along until you find and for every single output that you have, you compare it with your huge table of endpoints, and eventually you'll find the right endpoint. And then from that point, you have your start point stored in there, and so then you can just like start from the start point and calculate forward until you end up right before your endpoint that you're looking for. So, so it's kind of like if you think of it as a one-way function, it's kind of like just storing like different kind of place markers in between. And so once you find out where you are in between two place markers, you can start at one end and then calculate forward to find out what resolves to you. So that's the basic time-space trade-off. And the main problem with time-space trade-offs is collisions. Like, for example, with Landman, you have a password which realistically has only like maybe 2 to the 37 bits of entropy, and that's being mapped up to like 2 to the 56. And so you end up with tons of collisions, especially when you're mapping from 2 to the 56 back down to 2 to the 37. So a lot of people have worked on ways to try and reduce these collisions, because whenever you have collisions, you end up with huge overlapping chains inside your tables. And then there's also possibilities of loops where you have your thing endlessly go on forever. So one thing that was proposed to try and mitigate all these collisions is distinguished points, where you calculate your chain until you see an output that matches some sort of characteristics, like the last 10 bits are 0, or something simple like that. And then the one thing that's nice about that is that your endpoints can be compressed because you have a lot less bits in them, since all the last 10 bits are 0. And then you can also detect collisions a lot easier because you can just compare the endpoints, and that'll tell you if there was actually a collision that resulted in the same endpoints. The main method that people use nowadays is rainbow tables, and I'll go into like exactly how all these work. Essentially, rainbow tables uses a different reduction function for each link in the chain, and so the only way for actual merges to occur is for the index inside the chain to be exactly the same. The only problem with that, though, is it requires a lot more real-time computation, because you have to compute every possible like resulting chain from a given value. So at first we tried to use distinguished points because it's a lot faster than rainbow tables, and we assumed the A51 wasn't very collision prone, and it turned out that it actually was super collision prone. So we scrapped all that stuff and we tried working on some other stuff. We tried doing a rainbow table implementation, and what we ended up coming up with is we can build a table that takes up about 5 terabytes of disk storage, and theoretically, with one FPGA, you'll be able to reverse the key in about 5 to 10 minutes or so. And also, you can use multiple FPGAs to parallelize the cracking and make it a little bit faster. So with this, you can kind of like scale back and forth between how much storage you want to use and how long you want it to take in the real-time phase. And so we're still kind of working that out fully, but it'll turn out to be pretty quick if you have the right hardware. We also came up with this new method for doing stuff, and actually Steve just proposed this, and it's actually a really cool method that might be useful for other sorts of rainbow tables, where you combine distinguished points and rainbow tables, and so basically you have like you compute one distinguished point that is a lot smaller than the normal distinguished point that you'd want to use, and then you take that endpoint, apply a reduction function, and then compute another distinguished point, and then take that endpoint, apply a reduction function, and compute another distinguished point. And so it's kind of like merging the two together, and so you get the collision resistance of rainbow tables, and then also the speed of distinguished points. So that's kind of a cool method. We ended up messing around with it, and it turns out that it seems like we'll be better off with just using the rainbow table, because when we're spending months to calculate these rainbow tables, if we end up having collisions, it just multiplies the amount of time that we actually have to run the attack to get our get the amount of distribution that we need. So right now, the limiting factor is pre-computation. For actually computing 2 to the 58 with rainbow tables, it'll take about 100 FPGAs, 2 to 3 months to compute it. And then we also run into the problem with 4 to 5 terabytes. It's kind of hard to like really distribute to the public, and so we're gonna have to figure that out a little bit too. But we have actually already started building these rainbow tables, and we have proof of concept code that shows that they'll end up working once they're fully generated. And I can show you that right now, actually. So, let's see here. I'll show you. Okay, so this program right here will actually calculate a single chain on my computer here, just in software. So if we want to start at like just 1, it's actually running right now, and it'll take a few minutes for it to compute the end chain. And I could let this run if we have some time, or you guys can see me later, but it'll actually take a little while, so I'll just skip this. Now, oh wait, do I have that on here? Oh, I don't actually have the FPGA version of this on here, but if you guys want to see it later, I can show it to you. It actually computes hundreds of chains per second, so it's quite a bit faster than this version. So I can show you that. But essentially, once you run this, it computes a chain, and here's like a very verbose version of it, where you start out with this initial value, and that gets mapped to this one, and then we reduce it down to like this value over here that gets mapped to this one, and so on, and eventually you end up with the end of the chain here. So if we take, let's just take like this value. So let's say that the value that we have is this one right here. We can just feed that into this program. And this is using a really tiny rainbow table that I know that this value is in, but this is basically what the real-time phase will do. And it'll use an FPGA. And so what it's doing right now is it's taking this value and then hypothesizing that it's like, at the very end of the chain, and searching through all the tables that we have and seeing if it matches any end chains. And then it goes down, oh, it just found one, so it's recalculating. Oh, I already found it. Yeah. And then, oh, okay, here we go. So then it goes and it says, okay, well, what if this is the second to last value in the chain? And so it assumes that, calculates forward, sees if the endpoint matches, and that's actually what it did here. And so once it finds a matching endpoint, it starts at the start value, calculates forward right in front of it, and it finds the key that maps to it. So if you can remember 9B AAB, we can check out the mapping here. And there is 9B AAB, and so it actually reverses it back to the original value. And this will end up actually offloading this recalculation stage to the FPGA, so it'll end up being a lot faster when you actually run it. So the hardware that I'm using for this is actually just this little express card in my laptop, and this is what it looks like. It's got a Vertex 5 LX50 on it, and it's got some SRAM, and it uses express card, so you get 2.5 gigabits per second, full duplex. And this is pretty much the end of my talk. I wanted to give a plug for a party that we're running tomorrow at Camp Anaconda. If anybody wants to stop by, my conference TourCon is sponsoring all the drinks, and it'll be starting at 10 p.m., so you guys should check it out. Now, that's pretty much my talk. Do you have any questions? Go ahead.
Hi.
Hello.
Regarding the pre-calculation problem, there have been some work done, and one-way functions, and this works, use the Sony PS3. Did you study the possibility to use this device to do your pre-calculation and rainbow tables? Or would it be really feasible? Is it just a dream, or is it a real possibility?
To use which device?
What?
To use which device to pre?
The Sony PS3, the PlayStation 3.
Oh.
Oh, okay. Do we need to repeat that, or? Oh, he asked if it's possible to use the Sun or the PlayStation 3 for accelerating this.
Using a cell processor, I believe.
Yeah, the cell processors. I actually have some cores to crack RC4 with FPGAs, and a friend of mine, well, actually HD Moore, implemented the RC4 cracking stuff on the PS3 as well. And I think that my stuff gets around like 9 to 12 million encrypts per second, and his stuff gets around 1.5. And so it would probably end up, accelerating it a bit, but it wouldn't be, at the same order of magnitude as the FPGAs. But yeah, if you and your friends all had PS3s, you could probably pull them together and do something with them. Yeah, definitely.
Anyone else?
So why is this a public project?
That's right. Okay, this was the first question. Thanks for asking. Okay, it's not okay. Why is this a public project? There were a couple of other people working on this, and one of the persons who were working on this, you maybe have heard of it, Stron, and apparently he killed himself a couple of years ago. And then there was a guy from 2600 meeting in London who proclaimed that he has cracked A5, and he never showed up to the meeting again. And then just half a year ago, there was a professor from the university in Sussex who proclaimed that he has cracked A5 with a new idea, and he was supposed to speak at the InfoSec security conference in London, and GCHQ, which is the UK equivalent for the German BSI, basically told him, you're not speaking there. And I tried to contact him, and I sent him an email, and I got a reply from Mail-a-Demon. This email is not valid anymore. So there are a lot of people who got into problems for cracking A5, and we thought if we do it from the start, very public, and we involve many people as we can, it's much more healthier for us.
I'm sure we must have major questions here. Anybody? God.
Over there.
Back there?
Sorry? Where?
Behind you.
Oh, no,
No?
sorry. Thank
Oh.
you, sir.
Well, 2 to the 58 sounds a bit expensive. Using 2 to the 58 bits or whatever samples for the rainbow tables is a bit expensive, I guess, for storing that.
Well, 1 terabyte of hard drive storage costs €280. So you need 4 or 5 of these disks. So it's not that expensive when you think about it. It's €1,000 and you can crack A5. I mean, depends who you are, you know. You can share with people. You can share with other people.
Anybody else?
Pardon, I'm not sure if I did understand it correctly, but you are cracking the shared secret which is used for every transmission? Or is there any session keys?
We are cracking the session key. So even for the same mobile subscriber, every time he receives a call, we have to crack again.
Okay, thank you.
Okay, but when David was talking about that it requires 3 to 5 minutes to crack, this means the cracking itself takes 3 to 5 minutes. We only require a milliseconds of the conversation, okay? And that's a big difference to all the other academic papers. They say they require 3 minutes of constant traffic. We don't. We just want 3 GSM bursts and we are done. Cool.
Anybody else? Please.
There's one here.
Oh.
Third row.
Yep, sorry. Oh, thank you. Sorry.
Hello. I'm not quite sure if I understand it right, but the rainbow table actually acts as a database, does it? And so, is there any idea to make that rainbow table database available public on the internet? So not everybody have to buy 5 terabits of disk, but just one, or maybe a few people throw it together and just make it available.
Yeah, we could possibly do that. The only problem is that, especially like if you're using FPGAs for repeat the. Yeah, he was asking if it's possible to provide the rainbow tables publicly, like where people can like submit stuff and we do the reverse for them instead of having to distribute the whole tables. And we could possibly do that, but like a lot of our calculations assume that like you actually have a decent index in your RAM and you can do the lookups really quickly, and really all the time that you're spending is like actually calculating the chains for the lookups. And so so it's possible that we might be able to provide that, but it may not. It may take the cracking a lot longer to if we did provide it over the network. So it might be more worthwhile for you to just like get some drives instead of trying to do something like that. We still have to work on the details.
What is the current dollar investment in this project? The 100 chips and all the drives and whatnot.
Well,
could you just say that again for me?
Oh, what's that?
What did you just say again? I didn't hear what he said.
Oh yeah. He said like what the dollar investment is on the project so far. I'm not sure what the dollar investment is on your end.
Well, for the USRP, we got a special deal with Matt, who's designing the USRP. And in the past, if you joined our project, you got 10% discount, which was great. Thanks, Matt. And for the FPGA, I think David can explain more about the cost, how much they cost, and.
Yeah. I run this company called Precomputation, and so we make the FPGA boards that I've been using for this. And so the machine that we're using that has like 100 FPGAs in it, we'd probably end up selling for maybe around like $200,000. Where the current rainbow tables that we've generated use a 28 card cluster, which we sell for maybe around 60,000 or something, 50 or 60. So you can also get like off-the-shelf developer boards like the Gecko 3 or other FPGA boards and adapt our code to that, and it'll all be open. So whatever boards you have, you can port it over.
Yeah, the pre-computation stage is the only stage that requires 100 FPGAs or 28 FPGAs at the moment.
Yeah.
But later on, for the real-time attack, you only need one FPGA, and the cheapest board available, I think, is around $600.
Yeah, and the one that I'm targeting it for, we sell for roughly around $2,000. So roughly about $2,000 in hard drive space and then $2,000 in FPGA. You can be cracking stuff fairly quickly. Go ahead.
Yeah, I also want to ask about the FPGA, because on the USRP there's already a Cyclone FPGA. Did you try to run it on that? Can we use that? Because there are a lot of USRPs out there which do have an FPGA.
Yeah, it's possible to do that. The Cyclone 3 is a bit of an older FPGA, and you'd have to reflash it like after you do your capturing. I'm not too familiar with how the FPGA works on the USRP, but I guess it's possible you might be able to do that. The other limiting factor is the bus between the computer and the FPGA. Like right now, we're with this card we're doing 2.5 gigabits per second both ways, whereas if you're doing it over USB or something like that, it might be a bottleneck.
To save the cost of the 100 FPGAs to build the rainbow table, is it possible to use a distributed computing network like Boeing base of SETI at home to calculate this at our computers at home?
Possibly. Well, the calculation on a standard PC is dramatically slower than an FPGA, but with SETI at home you have dramatically more computers. So, if you know someone at SETI at home and we can, we can run our algorithm, that would be top. But yeah, it might be possible.
Yeah, we haven't fully optimized the PC version. According to some of the white papers, they've been able to get it to run at about 2 to the 22 per second. And we're doing roughly like 2 to the 31 per second on FPGAs. So it's about 500 times faster than a highly optimized, computer program. So if you have like thousands of computers, you might be able to, get somewhere close to it. But then you end up having to deal with network lag and stuff like that, and doing the lookups over a network server and stuff.
For our attack, you would need 50,000 computers, okay, to do the same speed as 100 FPGAs. 50,000 computers. But if you have them, that'll be great. I mean, City at home is 1 million computers. I could do it. Cool.
Anybody else? Anybody else? Would anybody else like to speak? You are completely sorted with this. Okay. Right, I'd like to thank these wonderful people for doing this.
Thank you. Good stuff.